let us go into the steps now. Now, I have told you the deoxidation is basically the reaction of dissolved oxygen with deoxidant which is dissolved, and finally creation of alumina in steel, which we want to remove slowly at the and finally go into the slag. But here is one problem. When we are tapping liquid steel from BOF or EF or induction furnace, at the top of the liquid steel there is slag. So, that means towards the end of tapping there is a possibility of the slag getting carried over from the primary furnace, that means BOF or EF, to the ladle. Because when we are draining out the liquid steel, there is a funnel formation. That means liquid steel which is coming towards the end of the tapping, the portion of liquid steel is less, on top of it there is slag. So, when there is a funnel formation, and along with the liquid steel some amount of liquid slag might be carried over from the furnace, that means from BOF or EF to the ladle. So, this carryover of slag from the primary furnace towards end of tapping has to be restricted. Why? Because as I have told you, this slag has very high amount of iron oxide. It is more than 20%, it can be 25%, it can be almost 30%. Total FeO, different types of oxides are there. So, assuming it is FeO, the amount is more than say 20 or 25%. So, if some of it comes to the ladle, that means it will react with the aluminium which is present in the dissolved aluminium or dissolved deoxidant which is present in the liquid steel. This iron oxide in slag will react with aluminium in liquid steel to form alumina. Moreover, I have told you that we have reduced phosphorus in primary steel making stage. Phosphorus, most of it has gone from the elemental stage in liquid steel to the slag, but the slag has about 3% P2O5. I am talking of the slag from the primary furnace, which has more than 20% FeO. It has some amount of MnO, maybe around 4-5%, and also about 3% phosphorus oxide. Now, this phosphorus oxide, if this slag comes into the ladle during secondary refining, this may react with aluminium. That means, after deoxidation, whatever aluminium is there, the soluble aluminium is there in liquid steel, phosphorus oxide in the slag may react, and you see the phosphorus will come back. We call it rephosphorization. So, it is called phosphorus reversal from slag to liquid steel. So, reoxidation of liquid steel and phosphorus reversal in liquid steel, these two will be possible if there is a carryover of slag from the primary furnace. Is this clear? Try to think over it, what is happening here. I have told that at the final stage of, that means towards the end of tapping from the primary furnace, when we are tapping liquid steel from primary furnace to the ladle, there is a possibility of some slag getting carried over from the primary furnace to the ladle. Now, the primary furnace slag is rich in FeO more than 20%, maybe 25%, maybe slightly more. It has some amount of MnO also. It has also about 3% or slightly more phosphorus oxide. So, this FeO can react with dissolved aluminium. Phosphorus oxide in slag, if it comes to the ladle from the primary furnace, it can react with aluminium in liquid steel. MnO, like FeO, MnO also can react with aluminium and give rise to MnO. In this process, what is happening? This dissolved aluminium in liquid steel is coming down. So, it is the steel is getting reoxidized, and what is the most potential element which will reoxidize first? Of course, it is aluminium. So, whatever FeO and MnO are there in liquid steel, they will react with aluminium in liquid steel and finally give rise to alumina. So, the problem is dissolved aluminium is coming down, phosphorus is getting reversed, that means phosphorus is increasing in liquid steel, alumina is forming in liquid steel. So, whatever alumina has formed because of deoxidation, more amount of alumina is forming, more amount of aluminium which was present as dissolved aluminium is coming down. So, what is the implications? If dissolved aluminium is coming down, because aluminium and dissolved aluminium and dissolved oxygen multiplication is constant. So, dissolved aluminium coming down means dissolved oxygen will increase in liquid steel. That means again reoxidation we call it. Phosphorus is also increasing, alumina is also increasing. So, again there is a possibility of, to certain extent, affection of cleanliness. The cleanliness is getting enhanced in this process. So, we have to be very careful about how this slag from the primary furnace can be stopped. I have mentioned here the decrease in dissolved aluminium will increase in dissolved oxygen in liquid steel, because the multiplication of aluminium and oxygen is constant, as I have told you earlier. So, what is important is use of effective slag stopper is essential. That means slag from the primary furnace BOF or EAF should not be allowed to be carried over in the ladle. It should not be allowed to come from the primary furnace to the ladle. So, what is slag stopper? Some of you possibly know. It can be two ways you can stop slag. One is you can put a refractory, some balls or something like that. We call it a dart, and the density of this is in between that of slag and liquid steel. The slag has lower density, that is why it is at top of the liquid steel. So, if the density of the refractory ball or the dart is in between slag and liquid steel, so whenever it will whatever, if it is floating, it will float at the interface of liquid steel and slag. So, at the time of liquid steel is getting tapped, it will come whenever slag tries to come near the tap hole, it will stop the slag from coming through the tap hole, because the dart will come to the slag hole or the tap hole, rather the tap hole. So, this is a way it can be stopped or to some extent controlled. Another way is, and technique, that whenever slag tries to come, a signal will be generated and the BOF will be tilted. That means you can control the slag coming in, you can detect the point where slag is coming near the tap hole and the BOF will be tilted back. So, this is a technique for slag stopping. This helps in subsequent stages of secondary refining, because if you have slag, primary slag, the attempt to enhance the quality is restricted to some extent. So, another requirements are basic slag and basic refractory in the ladle, because if you have a acid slag, that means if I have SiO2, then this SiO2 will again react with aluminium in liquid steel or dissolved oxygen in liquid steel, create SiO2 and generate some problems. Moreover, the slag also should be basic, so that alumina, when it is floating up, it gets absorbed by the basic slag. So, I have mentioned that we have to give adequate time to this alumina particles to float up. So, during deoxidation we are generating alumina. So, I have told you generation of alumina takes place very fast, but this floating up of this alumina, this takes time. So, we should allow some time, maybe about 20-25 minutes, for these alumina inclusions to float up during the secondary refining processes, so that whatever alumina is getting generated during deoxidation or during reoxidation, they should be able to float up. This also we will tell you in some details the basic mechanism, how does it happen. So, let us talk about the flotation and consumption of this aluminum oxide, consumption at the level of slag, basic slag. Now, I have told you these alumina inclusions are generating or forming fast. Now, they are trying to combine with each other. Why? It is called Oswald ripening. This causes larger particles to grow at the cost of smaller ones, because smaller ones means their surface area is more compared to the bigger ones. So, if the smaller ones combine to become a larger one, the surface area decreases. So, it is called Oswald ripening. That means, from the energy point of view, this is favored. So, smaller particles will combine and bigger particles will form. Now, these alumina particles, their density is less than ds, that means density of the solid is less than the density of the liquid steel. That is why they will float up, because they are lighter than liquid steel. Now, we know of Stokes' law. It basically talks about what will be the velocity of the solid particles in liquid. It talks about this velocity of the particles, they are dependent on the square of the size of the particles. R is the size of the particles, they are square, and also they will depend on the density difference between the liquid and the solid. That means, the lighter the particles, the velocity will be more, and the bigger the particles, because it depends on R square, the velocity will be increasing very much, it depends on the size. That means, the particles which are larger, they will have more velocity, that means they will float faster. So, we know that larger particles, they will rise faster, they will go to the top, and finally, if you give adequate duration during argon purging or other secondary refining processes, these harmful large NMIs. Now, we have to recall what I have told at the beginning, this large size NMIs are really harmful. So, these large particles, fortunately, they will, if they are in liquid steel, they will float up faster. From this we can get this idea from the Stokes' law, because the velocity is directly proportional to the square of the size of the particles. The larger the size, higher will be the velocity, faster the particles will move at the top. And why this particles are floating? Because they are lighter, their density ds is less than the dl, that means the density of the liquid. So, these particles, whatever smaller particles have formed or nucleated, they will coagulate, that means they will come together, the larger particles will form, and it is known as Oswald ripening, and these larger particles will move faster, relatively faster compared to the smaller ones, go to the top, and if we have a basic slag, alumina will be consumed by the basic slag. So, this way we can reduce the quantity of alumina which has been formed by deoxidation reaction. So, I have told you what are the stages of deoxidation reaction, what is the criteria of knowing which element is a strong deoxidizer. This depends on the deoxidation constant, I have told you, K, and since the weight percent of the deoxidant soluble in metal, liquid steel, that particular metal, aluminum, calcium or silicon or whatever it is, or manganese, and the weight percent of oxygen, the multiplication of this is constant at a particular temperature, which comes from the free energy values. So, we have told why this K values being very small, relatively small compared to K values of silicon or manganese, the small amount of aluminum will be useful to reduce oxygen to a very low level. So, whatever is forming now, say aluminum we are using mostly for getting very low soluble aluminum for good killing of steel. Whatever alumina particles will be forming, they will try to combine together and they try to float, because first thing they are lighter than liquid steel, they try to float, and whenever their particles are combining with each other, larger particles will float faster, the velocity of floating will be more compared to the smaller particles. So, larger particles will float, come to the slag, will get absorbed by the slag if we have a basic slag. So, this deleterious large deoxidants, alumina particles which were formed because of deoxidation, they will be consumed by the liquid slag. So, thereby the inclusion level is coming down, because by deoxidation we have taken care of the soluble oxygen. Now, whenever these alumina inclusions are forming, if they are also taken care of from liquid steel to the slag, that means the liquid steel now becomes low in soluble aluminum, low in alumina or other oxide inclusions. That means oxygen present in liquid steel as soluble element as well as oxides or inclusions is combined also is coming low. That means the total oxygen is coming low. So, that way we ensure that the cleanliness, oxide cleanliness of the steel is also enhanced. So, I have tried to mention to you what are the secondary refining processes, what are the expectations of secondary refining. I have told the first and foremost requirement is deoxidation. So, this is required and this is ensured by all types of secondary refining, whether it is LF, whether it is VD, whether it is VAD, whether it is VOD, whether it is argon gas purging, whether it is injection metallurgy, whatever you are doing, whatever process you resort to, deoxidation is the first step, because the soluble oxygen has to be brought down in liquid steel. And in this process you are bringing down soluble oxygen, and also the deoxidation product, if it is alumina, you are trying to allow these inclusions to float up, giving sufficient time, putting argon gas as a purging gas from the bottom of the ladle and trying to facilitate the inclusions, alumina inclusions to float up and get absorbed by the basic slag. So, in the process dissolved oxygen as well as oxygen as oxides in liquid steel are coming down, the total oxygen is coming down. So, the cleanliness level is enhanced in this process. Next, in subsequent presentations, I will talk about the other requirements, how they are fulfilled in secondary refining, like desulfurization, degassing, so shape control of oxygen, control of the melting point of the oxides and related issues. Thank you very much.